Oh, sorry, last Thursday if you happened to miss the message on Slack. I should have sent an email out as well, but I was not capable of coming in. I was barely here on Friday just for one class, but it was a rough day. Um, so if you happen to show up, I apologize. I mean, it's funny, but I apologize. How many of you did show up? So you didn't check Slack?
I was supposed to get notifications for whatever reason. It never gave me a notification
Oh,
on that one.
well, I did post it on Slack. Well, I should have. I should have also sent an email. I think I posted like at 3 in the morning. Like the
Yeah,
night
I
before. The night before was really rough. I had class here, and I threw up in class. It was a rough one. I don't even know what happened. I don't know if it was food poisoning or whatever. But I was kind of thinking, oh well, maybe it'll pass, and by the morning I'll be okay. So at 3 in the morning, it was pretty clear it was not going to be okay.
if I go and find the recording of that class, are you gonna be
What you see is you see me. I tell them leading up to them, like, I'm just not feeling so hot up here. And then I go up and say, okay, where's the pause button? Where's the pause button? And I hit pause and I like dart out of the room. And I'm in there for 20 minutes in the bathroom puking. Nobody came and checked on me. They're all the students are like Indian, Pakistani, Saudi. So they're very like respectful. Nobody left their seat. So I come back in 20 minutes later. They're all still sitting there. I mean, I could have been dead in there. Who knows? I wonder how long. What's like when class is over? Would they've even checked? I don't know. I don't know the answer to that. Yeah, I don't know. That was it was a tough one. Okay, so let's see. Your homework that was due on Thursday was to reverse the A list, right? And then for today was to do a quick sort on the A list. Does that sound accurate? Okay. So let's talk about Quicksort and the algorithm for Quicksort today. So do I have a sample of? No, I'm gonna have to make my own array here. And just so we have the example with an odd number, give myself one more. All right, let's put some values in here. So we'll say 4, 2, 8, 1, 3, 7. Put another 7 in there. 6, 9. Okay, so we have some. We have an unsorted array. How does Quicksort work? How does Quicksort ultimately sort this array? Take me through the algorithm here. We all should have written it, so we should at least be able to describe it. Okay, so we start with this guy. So we have to figure out what you pick a pivot. How are we picking a pivot?
It's usually picked as the midpoint.
Okay.
I think. Well, that's how they usually represent it in the book.
Okay.
Yeah.
So we're selecting a pivot. You're suggesting maybe a midpoint. Okay, so this is one difference already from merge sort. In merge sort, it's really supposed to be the midpoint. Quick sort doesn't really have to be.
Okay.
Quick sort, in fact, there's a performance argument to pick the pivot as the last element, far right.
I think in the Wikipedia they said that if you pick the
That gives you the best performance, and it also gives you the risk of the worst performance. Yep. So that's one of the arguments for quicksort is that it can be by far the best, but it could also be significantly closer to some of the weaker sorting algorithms. you know, and after we kind of write it, we'll talk about maybe why we would still choose this. Okay, so you're suggesting a pivot. Now you mentioned high and low. Tell me about that.
It's the high and low index where it's counting, where it's still take the low element in the array, compare it to the pivot, right? And then if it's greater or less, if the pivot is less than that low index, it'll switch it. It just runs through each way both ways.
Okay, so you're saying we need three pieces of information.
Right.
We're picking a pivot, picking a spot.
Yep.
All right. Then you're going to figure out what where the position of the lowest thing in the array is.
Yeah.
And then what the position of the highest element in the array is. So we need those three deals. Okay, let's start with that. So you want to pick the center guy for your pivot. Fair enough. So is that 3-ish? Yeah, looks good. All right. So let's give myself. Let's give ourselves an index here as well beneath this. And obviously, indexes are always orange. So this is 0, just so we can reference. Okay. So here's our pivot. And we're going to keep track of the position of the pivot and then reference the position of the pivot, right? So give ourselves this 4 here. So we pick bucket 4 as our pivot, which happens to have the value of 3. All right, then the position of our low value, we can just pick out of the crowd here and say, okay, well, that's this 1 here, right? Okay, so that's bucket 3. So we'll give ourselves a variable for low. My copy and paste performance is too fast for this computer. Nailed it. All right. So low is bucket 3. And then we're going to need a high. Which is bucket 8. All right. Do we need anything else to get the ball rolling? Is that good enough for right now? Okay. So now what do we do? So I've selected a pivot at random. All right. Center is as good as anything else. Center is probably going to give you the best average performance. It's kind of your deal with that. All right. Now, just out of curiosity, and I don't want to get too much into the actual implementation of this now, but how would you have gone about determining high and low? I mean, as humans, we glanced at it and said, oh, well, the 1 is there. That's the smallest. And then there's the 9. How do we determine it? What if 7 had been the highest? Which bucket would we have picked for 7? It wouldn't have mattered, but how would we go through and figure out the high and the low?
5, 0, 1, 2, 3, 4, 5.
So it's a linear search, pick the winner? Because by definition, our data is not sorted, or very likely is not sorted, right? So we can't use any of the fancy search algorithms for determining whether or not what the smallest and largest value is. So, well, fancy would just say check bucket 0 and check the last bucket, and then we're just going to say we're done because the data is already sorted. But we would just go through and do a linear search, but do double time by looking for smallest and largest value, right? Okay. All right, so I have these things. Now what do I do? Do I need to loop through some stuff? Because what is my ultimate goal here? What am I trying to do?
Trying to arrange everything in order.
Okay, well, ultimately I'm trying to arrange everything in order, but in terms of the next mini step, what's my next step in Quicksort? What am I attempting to do?
Break it into smaller partitions.
Okay.
Well, find where one bucket is supposed to be in one of the partitions and then.
Okay. So what do you want me to do next here? So I've taken my original data, I've picked a pivot, I've figured out a high and a low. What do I do with those 3 values?
Total population. Part 2.
Okay, what does that mean? I'm going to start splitting this thing up into some chunks.
Yeah.
Okay, how am I going to split it? And do I need to do anything before I split it? So there's a distinguishing, there's maybe a big difference between quicksort and merge sort is what happens in the various steps. So merge sort, we split our partitions up, right? We split our list up, whether it's a linked list or whether it's an array, doesn't really matter. Ours in this case is going to be an array. We split it apart, and then our merge step is where a lot of the logic is occurring. With quicksort, most of our logic is actually occurring in the divide and conquer step. You know, when we're dividing it up, we're doing a lot of our logic, our reordering then. And the recombobulation step actually does nothing, right? You know, that just is kind of letting everything snap back together and say, ta-da, everything's good. Right, so that means when we're partitioning this, stuff probably should be happening, right? What's the stuff? Okay, so what am I doing next in this algorithm? Keeping in mind that we all wrote this. I tell you, we found some really good Java implementations on the Google.
Even in the book, they just gave you the code for it.
Yeah, we should still understand it, right?
When I was actually trying to understand it, I thought that this picture I'll mail out. They had that on Wikipedia, where like every time the pivot is shaded.
Oh, okay. I got you. I might bring it up in a few minutes. All right. So I've done your first 3 steps you told me to do. What do I do next?
So we want to move the pivot to where it's ordered in the sequence.
Okay. So you want this, in our case, our pivot's location is 4. So we want this 3. We want this guy to ultimately get to where he should live, right? Because each time we're pivoting, kind of the goal for that pivot is relocate this dude to his final location. Isn't that what happens? Everything else might still be in flux, but when we pick a pivot, what we're effectively saying is, I want to move this guy to his final location, and it's his turn. Okay, and how do we do that?
Comparisons.
Okay, well, specifically. So I know this is the dude I'm moving. I know I want to move him such that everything to his left is less than or equal to him. Everything to his right is greater than him, right? Well, no. Left, right, left. All right, so how do I go about doing that?
You compare him with index that you start with, which usually is the first index in the array.
Okay, so we're gonna
The value in bucket 4 less than the value in bucket 0.
okay. So we have a 3 compared to a 4. Is it less than that? Yep. So what do we do? Swap it. All right. So we're gonna move our 3 there. Oh, well, it used to be there. 4, 3 there, and 4 there. All right. Now what? And just so we have our original values, we'll do a 3. Since I'm doing some swapping, let's just preserve our original values here as well. So I had a 3, I had a 1, and I had a 9. Okay. Now what?
Then you move the low index up.
Okay.
So it becomes, so from 0 it becomes 1 now, so then you compare with.
Okay, so now, so you want to, we just moved this guy. So now what do you want to do with his low index?
Point the next one up in the
All right, so you want, instead of it being bucket 3, you want it to be bucket 4?
No, see, I would have had the low index be bucket 0.
array. Right.
Because it's not of the lowest object, but it's of where I'm starting.
So lowest position, not the lowest value.
Yes.
Okay. So we had these guys wrong. So you would have said 0 to 8. So the 8 was correct, but correct for a different reason, right? All right. So this happened to have a 4 there. This happened to have a 9 there. Okay. So now you want to move low up 1 because is it because we just replaced the low, or is it just we always would naturally increase low by 1? What's the rationale for making low 1 bigger than it used to be? Go ahead. What's the next set of numbers going to be? Okay, I guess what I'm saying is the next set of numbers being the high and low of the new partitions, right? Okay, so you want to take low and move it 1 higher than it used to be. So you want this guy to now be a 1. Okay, do we do anything with high? Leave high alone. Okay, so now I've relocated our pivot. Okay, we happen to do that on our first try, correct? And we moved him into bucket 0 because that was the swap. Is that the last move we do for him? We're just getting started, right? All right, so now we increment low by 1 because we've already compared. So when we went through here, we started at bucket 0 and we're going to bucket 8. We're starting at bucket low and we're going to bucket high, correct? And each time through, what are we comparing? The pivot value. All right, so now we're still going low to high. All right, now realistically, when we write this, we probably wouldn't have adjusted low. This probably would have been inside of a for loop where we would have started from low to high, and low would have naturally increased probably on a counter on high or something like that. And we'll write that, but the idea is for us, we're comparing within the right range. So now we're saying this value here, I want to compare him to my current pivot. My current pivot actually lives at bucket 0, right? And the value is 3. So what comparison am I asking? Should be the same comparison, right? Should this guy is this guy less than or equal to my pivot? Is 2 less than or equal to 3? It is, so we swap them. Okay, so there's our 3, there's our 2. Then we'll increment our low because we're moving down here. So now we're on this guy. Should an 8 come before a 3? Nope. Increment. Should a 1 come before a 3? Yep, swap. There's our 1. There's our 3. Now we're here, right? But that's actually our pivot. So what do we do?
Start looking at the path of the...
Okay, but do we do any logic on the pivot? So I happen to just swap the pivot with where I currently am. So now, well, I guess we'd always do that. So now, we're incrementing, right? So now we're incrementing by 1, so now we're here. So should a 4 come before a 3? No. Should a 7 come before a 3? No. Should a 7 come before a 3? No. Should a 6 come before a 3? No. Should a 9 come before a 3? No. So now we've gone all the way between low and high. And what can we say now about our pivot? What could we say with confidence right now about our pivot? It's where it should be. It's where it will be at the very end when this thing is successfully sorted. Okay, great. Now what? So we've done some internal rearranging. Okay, whatever you want to call it. So everything to the left of our pivot now we know is less than or equal to it. Everything to our right of our pivot is greater than it. And we know that our pivot is currently where it needs to, well, not currently. Our pivot is in its final location, right? So we don't even have to worry about our pivot again. Now we're looking at rearranging things before the pivot and rearranging things after the pivot, knowing that things before the pivot are already on the correct portion of the list.
Why is there an
Who?
8? An 8.
An 8? Oh, sorry. What was that supposed to be?
I don't remember what that is.
Oh, great. Yeah, great people.
I just know I've been looking at the 8 for a while.
Oh! I didn't swap it out. So we had it here. Okay, so where are we at here? So this is okay. This is now we have our low is right here. So should a 2 come before a 3? Yes. So we'll swap. There's the 2. There's the 3. Increment by 1. Should an 8 come before the 3? Nope. So do we do anything to it? Nope. Should a 1 come before a 3? Yes. So what do we do? Swap. Yeah, see, this is the swap that didn't happen. So what happens right here? Does that mean that step wasn't done? Because in all these other ones, we said, here, if I go back one more step, this is our low right now. Should a 2 come before a 3? Yes. So we swapped. And then we stopped right there. Do we ask any more questions? After we say, should a 2 come before a 3, we swap. But low is still right here. Is there any other question to ask right now? We would say no, right? That's how we've been operating. Then I say, so we increment by 1. So this is our low. Should an 8 come before a 3? No. Should a 1 come before a 3? We're saying yes, but the question is that the question we're supposed to be asking?
How I saw it done was at that point, once we determined that the 8 didn't come before the 3, is instead of moving the low index up, we start moving the high index down.
Okay.
And so then we started from the other side, asking did they come before 3, which I think would end up
Okay. Fine.
possibly taking care of a problem.
All right. So we stopped here. Yeah, we're in the right place. So we hit something right here where we said, okay, well, an 8 does not come before a 3. So we've gone as far as we can from the low side of things. This will change the implementation a little bit because now we won't have that natural for loop that just goes from low to high. That's okay. It's okay for as long as we're accomplishing the ultimate task. So now you want to start down in this end. So you want to say, what, should a 9 come before, you're comparing it to pivot still? Okay, should a 9 come before a 3? No? And so now it's the opposite logic. So we're saying that's good, right? So then we say, should a 6 come before a 3? Should a 7? Should a 7? Should a 4? Should a 1? Yes. So what do? We swap the 1 and the 3. Okay, well, so that's the same thing we just did before, right? There's the 1 and the 3.
And now we take the high down one more.
Okay.
So now we compare this to 3. Does the 8 come before 3?
Okay.
And it does.
Gotcha. So you hit the crossover.
Right.
You hit the okay, fair enough. So now you can do the swap there. So now, okay, so we can say that would work. And we know that we're done once low and high are once low is greater than high. I think it would be greater than. I don't think it'll be equal to because I don't think it would ever actually be equal to. But whatever, we'll figure that out when we actually write it. But if we go back, because obviously the more natural approach to this would be, let's see, where are we at here? Okay, so we'll do our initial swap, 2 and 3. Then we'll say, should a 8 come before a 3? No. Should a 1 come before a 3? No. Or yes. So we would do the swap, but that put us out of order, right? So right here is where we had our initial problem, when we were going from high to low, with an ultimate goal of having a single for loop that just takes us from low to high and does all the swapping. So we're currently sitting right there for our current value of I in our for loop. But the issue is that we just passed that guy. So we said, should this be swapped with a 3? And we decided no. So we moved on to that 1, and then we did the swap. How could we handle this 8? In a way that would be consistent, not that would just work this one time. think we can almost look at this like a hybrid type of approach. If we look at this 2, up to this point, we've always said, I'm going to compare the 2 to the pivot and do the swap. Is it unfair to say I want to compare the 2 to the guy right before it until I get to the pivot? And we're going to swap as many times as it takes until I get there. So in this case, the guy right before it happens to be the pivot. So I do my swap. So there's my 2. There's my 3. Then I increment. Should an 8 come before the guy before it? No. So I'm done. Didn't even have to ask the question, was that the pivot? Should a 1 come before the guy before it? Yeah. So I can do the swap. Am I at the pivot? I'm not. I didn't just swap the pivot. So I'm not done with this 1 yet. So now I can say, should this 1 come before the guy before it? Which is the 3, which is our current pivot. So I'll do the swap there. Now I can say I'm done because I just swapped the pivot. Right? Okay. Does that put us in the correct position yet?
Nope.
Now what? Well, does this put our pivot in the correct position? All right. So is the state of this current list the same as the state would be with you starting at high right now? Okay. Are there any problems with what we just did? Because that was kind of we let the things bubble towards the top. It's kind of a hybrid approach to it with using a for loop. Both of them are reasonably valid. I think that the challenge in this side of it, the way I just presented it, is making sure you keep track of, is the thing you just swapped the pivot? All right, so that's where you are keeping track of location of pivot as well as value of pivot. Because you could have multiple values in your array that match the value of the pivot. So you can't just compare the value. You have to say, did I just move the pivot? Make sense? So you got to keep track of the current location of the pivot at all times. So either of those approaches will work as long as ultimately you put your pivot in a place where everything to the left of it is less than or equal to it, and everything to the right of it is greater than or equal to that. Is it a true statement right now? Yep. Okay, so what's next? I know this guy is good. This guy is done. We can, if you want to do some color coding stuff, we can go ahead and mark him in red. Okay, not going to shift him again, right? He's done. So what am I going to do now?
Now we need to sort everything before the pivot and everything after the pivot.
Okay.
So we could.
What algorithm do we use for that?
Quicksort.
Same one we just used, right? So I need to do what I just did to this part, and I need to do what I just did to this part. Okay. So here we'll go the easy route first. Okay. Remember, this is being passed by address, right? So we're working with these arrays in memory. Okay, so I'm giving you a little snapshot of memory here. So we're going to call this guy, and we're going to have high and low. Low is going to be 0, high is going to be 1, right? And in this case, we don't need the value since we're doing the for loop that's going from high to low, including high. And so then once we're here, we pick our pivot. So it's kind of a pick your poison thing, right? Part of this I mentioned a little bit ago about that it's pretty common to pick the far right element as the pivot. There's actually 2 reasons for that now. Anybody? So one reason is, one reason it would be a pretty easy pick for the pivot, right? Because if you remember from merge sort from last semester, one of the challenges is to find the middle is sometimes a little bit of a math hack. Where is it the exact middle, or is it +1 from there? So you kind of make sure your math is correct from your relative starting positions. Where if you always pick high as your pivot, that's kind of easy math, right? What's the other advantage? based on the conversation we've had over the last 5 minutes. If pivot is always at the end, will we run into some of the same differences that we might between my approach of going for loop directly through and her approach of starting low to high? You actually still can, but it should be less common for you to have issues where you start at the end, have to go and start at the end. So there's some advantages to this, but we also mentioned at the earlier on, the disadvantages is that you are risking a slower sort time. But with any of these, since we're dealing with recursion and splitting these things, we can benefit search time by doing what? Because when we talked about recursion last semester, what's the problem with recursion? Besides you don't like it. What's the weakness of recursion? Why don't we just choose to use recursion all the time? Recursion completely non-destructive, has no downside to it whatsoever. When we call a method recursively, we're putting the current call of that method on hold, which means we have to store all the information about that method. Okay, all the memory, all the variables for that particular call to it, we got to pause. And we throw that whole thing on a stack and say, okay, we'll come back to you soon. Or sooner rather than later or something like that, right? And then we start over. So we get new copies of all the variables. We get new copies of everything. And we work with them until we call that recursively, and then that recursively, and that recursively. We probably looked at an example of a stack index out of bound or stack index overflow error or something like that last semester when we were looking at the recursive version of factorial. If we wrote it to be an infinite loop, so to speak, where we never actually ended, we'd eventually run out of stack space in Java because we kept throwing a copy of the current variables of that method onto the stack until the stack just ran out of stuff. All right, so recursion is working with a smaller memory footprint. When we're using normal, we could say we're always working with a smaller memory footprint with Java. But we're working with an even smaller memory footprint with recursion because now we're using a subset of the memory that the Java virtual machine has given us. Java is always working with a smaller subset of your total memory because the Java virtual machine is going to say, okay, well, you have 16 gigs of RAM. I'm going to let you use 1 gigabyte of it for your program unless you tell me otherwise. There's some command line options you can give to the Java virtual machine to have it behave differently than default. But you're always working with a subset of the everything. But we can certainly assume if the Java virtual machine has a gigabyte of RAM to work with, let's just use that as an example. I think actually it's substantially less than that is the default. It might be like 100 megabytes or something like that is the default. But if it's given a gigabyte and it has to set aside enough memory for a single stack data structure to support recursion, and we'll talk about stack data structures, with that in mind, we might say, okay, well, that's certainly going to be less than the 1 gigabyte, right? Maybe that's a 10% of it or something like that. So we leave the user enough space for their variables and that kind of stuff. Okay, so recursion is considered to be memory inefficient. Okay, it's very prohibitive to memory. That doesn't mean it's bad, because often recursion can be provide very elegant and short solutions in terms of the amount of code we have to write. And the second half to this is recursion we can say it's kind of evolved over the years. One of the things we're concerned about with merge sort or quicksort is memory performance, not just speed, because they're both heavily reliant on recursion, right? They both have 2 recursive calls in them. Right here, we know we're calling our quicksort on this half, and we're going to call that same quicksort function on this half. 2 separate calls to quicksort with just different highs and lows, right? So that's 2 places on that stack. two memory locations, even though the second guy won't get called for a little bit. He's kind of waiting to actually get his call because he has to wait for this guy to finish. All right, but punchline is it's a double recursion. What can we do with merge sort and quicksort that we know about today as computer programmers that greatly benefits the speed of this type of thing that really wasn't on the table years and years and years ago? Is it fair for us to say that this side is completely mutually exclusive from this side? They have nothing to do with each other right now, right? They are completely separate problems. They're ultimately going to come back together and be part of the ultimate solution. But these guys are not reliant on each other at all. Is there anything that says that I can't solve this problem and he can't solve this problem, and then we get back together in a little bit and share our results? That's fair, correct? So one of the things that we have now with kind of the advent of distributed computing, or maybe the baby step towards that would be multi-threading, especially now that you have computers with multiple processors in them. So you can do multi-threading or multi-processing, which there is a difference there. You talk about that probably in the operating systems course, but a thread isn't necessarily guaranteed to be scheduled on a different CPU, where a process should be scheduled independently. I'm explaining this poorly. A thread shares the CPU time of its parent. A process gets its own CPU time. So if we take this quicksort and we split it into two processes, this guy gets full CPU time, this guy gets full CPU time, and this guy might get CPU time on this CPU, this guy might get CPU time on this CPU, and then they are truly happening concurrently. If we have a thread and we split it into two threads, these guys are children of the parent process, and they actually share in that parent process's CPU time, total time they get to work on the CPU. Now, modern operating systems do have some strategies for allowing, a baby thread to get some time over here on a different CPU when it's available. So we're not completely screwed going multi-threaded, but in fact, actually, I think in most cases you'd be better off going multi-threaded because processes are heavyweight, threads are lightweight, and we're right back to the whole memory problem and that stuff. But that's an operating systems discussion. But from our perspective, if we can split the work as a computer programmer, and give it a chance of running simultaneously, running concurrently on the CPU, then our recursive calls block less, and we also then run into less problem with the stack. Because what we'd actually do is we would replace our recursive calls with creating a new worker for us to go and do this part of the problem, rather than a recursive call. So we'd actually not even use the recursive stack. But we're not doing that right now because we're learning about the recursive stack, so it's, that's out the window. But that's kind of the rationale behind why these algorithms are still very viable, okay, because of how they could be implemented. We're looking at the traditional implementation of these guys. Okay, so we're looking at our first recursive call, right? Our second actual call to quicksort, because the first total call to quicksort was on the original. Okay, now we're looking at our second call to quicksort, our first recursive call. So we're going to pick a high and low, which is going to be bucket 0 and bucket 1. We're going to pick a pivot, and I mentioned that the easy pivot choice often is set pivot equal to high. Now, one thing you have to do here, though, is we need to be consistent. Okay, so we started off by setting it to middle. So with that in mind, how did you calculate middle here?
Lowest bucket versus highest bucket divided by 2.
Okay, lowest bucket versus highest bucket divided by 2. Okay, lowest plus highest divided by 2. So 0 plus 1 is 1, divided by 2 is 0.5, which would be truncated down to a 0, right? So in this case, using the identical algorithm we used initially to come up with middle, we would actually pick a pivot of 0, which is okay. Any pivot we want is fine. And Quicksort, it just might have some ramifications on our ultimate performance of the Quicksort, but computers are fast, who cares? It's is what it is. In almost every case, Quicksort's going to beat the crappier sorting algorithms. So is merge sort. So really the concern happens to be when you're dealing with very large sets of data, now you got to start being a little concerned about memory. That's the real kicker with merge sort or quicksort. I usually look at them as relative equivalents. What I find interesting is that most research kind of shows that merge sort is at worst at least as good as quicksort, and in many cases faster than quicksort. Yet it's interesting that many implementations in programming languages use quicksort as their default implementation. It does kind of sound quicker, right? With the
like if we're talking about again, if we're bringing up like
uh-huh.
Merge sort's worst case scenario is the same as quicksort's average.
Yeah, that's what I just said.
Yeah.
Is merge sort is under almost every circumstance at least as good, if not better, than quicksort. Yet quicksort is almost always. In fact, I can't think of a modern language whose built-in sort isn't a quicksort. There very well might be. I know my knowledge seems vast, but there are limits. Okay, so but quicksort is quite common as the built-in sort in languages. I'll probably circle back and ask you why after we've finished this implementation, because there are some legitimate reasons why. Okay, so we picked our pivot using the exact same algorithm we used to pick our pivot before, because we're going to have to write this thing, right? And if we're going to write this thing, we can't just be all over the board on how we pick our pivots. So you decide how you're going to calculate your pivot, and you stick with that. So we did that. Okay, and I'll go ahead and say that's our current pivot value is our 2. All right, so then, again, we have our for loop that's going to go from low to high. Okay, including high, because we want to make sure we check this bucket, right? All right. Now, in this case, low is the same thing as pivot. Does that mean we handle it anything special? Well, remember, the algorithm that I kind of tweaked is I said, we're going to compare low. Imagine that we have I equal to this, then I equal to this, because it's a for loop that's taking us between low and high, including high. So this is going to be bucket I, bucket I, bucket I as we go through there. So I'm saying, is bucket I less than or equal to, or should bucket I be swapped with bucket I minus 1? Bucket I minus 1 is going to be a tough sell in this case, right? So there's no swapping because there's no question to ask. So that should tell us right there, maybe put a little note down that I'm going to have to, as part of that check, the swap check, I need to make sure I actually have something to compare beforehand, okay? And note there that I didn't say, should this guy come before pivot? Should this guy come before the guy right before him? And then if I do the swap, then I ask the question, am I done? And I'm only done if I've actually done my comparison with the pivot. Otherwise, I got to keep trucking to get this guy nudged as far over as he's going to go. Okay, so in this case, there's no comparison there, so we're going to increment I. Now we're here. Should a 1 come before a 2? Yep, so we're going to swap those guys. There's our 1. There's our 2, and just so we see what's actually happening, that has side effect because this was passed by address. So there's our 1. There's our 2 that changed in the original. Makes sense? Because these guys, the memory was passed in. All right, then I asked myself the question, am I done? Did I just swap the pivot? I did. Just swap the pivot, so I'm complete with that one. All right, so now my for loop is done, and what do I know? I know that my pivot is in its correct location, this guy. Am I done with this call to quicksort? Has he done everything he's supposed to do? Yep. And because of that, I can now solidify my pivot, which was this guy, as being in the correct location. So we'll go ahead and mark that. And this call to quicksort is now done. Now we still haven't gotten to this call to quicksort. Because what happens? Let's go back right here. I'll color it. So I'm like this. I've positioned that pivot. I need to now make 2 more calls to Quicksort. Well, up to 2 calls to Quicksort. How do I know that I need to make recursive calls to Quicksort again? How do I know that I'm not done with, for all I know, this call to Quicksort, this was my original list. That's all this guy cares about. His job was to sort this, what was handed to him. This memory address from bucket low to bucket high. That was his job. Okay? Go ahead.
It doesn't know if the thing below it is sorted or not, even though it's just
Okay, well, so we could say generically, since high and low are different values, here, we're not done. This is not a one list. Remember back to merge sort, we would always ask, is this list trivially sorted? And it was only trivially sorted if it was a one list. You know, if you only have one thing, it's by definition in order. Lucky us, right? So since this guy is not a one list, we need to sort again, correct? So in this case, we're not necessarily going to make this determination that we actually know that this 2 is where it's already been. Okay, we could say I'm going to save myself the microsecond recursive call to that second half because we happen to know that that this guy is that this guy is already in his correct place. But if you remember back to our original call, we called merge sort on everything before the pivot point, right? So we're going to call merge sort on this guy, what I have highlighted. Well, I wonder what weird combination of magic I just clicked. I hit like a bunch of things at once. Nothing changed on the screen, but something popped down, like the surprise. Awesome. All right, so I know for sure I'm going to be calling Quicksort on that part. But I'm also going to try to call Quicksort on everything that comes after this, which in this case is nothing. So this is going to result in a single Quicksort call. Okay, not because we're treating it as a special case. We're using the exact same algorithm. Call Quicksort on everything before, call Quicksort on everything after. Just so happens that after is nothing. Okay, so I still haven't returned from this original call. So I'm still stuck in that first original call to this guy. I've just gone ahead and marked this guy up here. So I've called Quicksort on this guy. I start from high to low, I pick my pivot, blah, blah, blah. Now I probably could expedite this by throwing in a little if statement at the beginning and only doing all that jazz if low and high are different values. If high is greater than low, that kind of thing, right? Because right here we can just say, look, high is not greater than low, therefore this must be the one list, which means that anything I do here is a complete waste of time. So we can just return. All right, that would be a little place where we could speed up the algorithm. Okay, even though we're asking a question, we're asking less questions than we would be otherwise when we know we're wasting our time. Okay, so now we've bounced back to this, which also says that we have done what we need to do with that guy, right? So now we're done with this. So now we've actually completed all of our Quicksort calls for the left half, even though when we originally called Quicksort on this left half, you know, we had 2 Quicksort calls. We had a Quicksort call here. We had a Quicksort call here. That guy hasn't even begun yet because it's been waiting for this dude to complete. If we had multi-threaded this or done this as a multiprocessor or even faster, done it as a distributed computing platform where we're actually split across multiple computers, you know, they would have been happening simultaneously. But because we're doing this traditional recursion, we had to wait. So this guy hasn't even started yet. So we called it on this. We did our logic there. Then we called it on this part. We did our logic there. Finally, we were done. We had no left and right to split on or anything like that. So we bounced back and we're done. Okay, with that part. So finally, we get back to our third overall call. to Quicksort. But he's not happening number 3. He's actually happening, number 5 in the list. So, man, you really got to be explicit about that cut and paste thing, or copy and paste thing. All right, so now I've called Quicksort on the right half. Now we can glance at this and see that we're probably going to have to do a little bit more work on this side, right? It's a little chunkier over here. All right, so we pick our pivot. You said we're going to take low plus high divided by 2. All right, let me go ahead and write down that little formula. Pivot equals low plus high. Do our parentheses dealy flippies. Divided by 2. Okay, so low is 3. High was 8 for that guy, right? And that would have been passed into our Quicksort call. So our call to Quicksort needs to know about high and low and the array. So here's the memory address where you can find my stuff, and then where to start and where to end. That's the little window we're looking through. Okay. So pivot equals low plus high divided by 2. So that's going to give us what? 8 plus 11 plus 3 is 11. 11 divided by 2 is 5.5. So 5. So bucket 5, which is a 7. All right. So then we're going to start a for loop. Let me just give myself, since I keep losing track because I'm old. Current value of I. There we go. That way I can just move the little box. Trust me, this will help me. You should always draw pictures too. If it's helping me, it should help you. And me, it's senility. Your brains are young and fresh. And you're just ready to go. I have a reminder on my phone to brush my teeth in the morning. Also a true story. Isn't that sad?
I always wondered if the sticky notes over the light switches was a real thing.
It is. Yeah, he helped another student watch my house when I was in Florida over break, and so in my house, all of our light switches have Post-it notes over them, which looks like crazy people live there, right? Well, for Christmas, so actually it was before Christmas. It was my wife's birthday? I don't know, for something. My wife asked me for hundreds of dollars worth of the Philips magic light thing. You know, you talk to Siri and lights come on and off and bright colors and things like that. I mean, they're like a 3-pack is like $100 and some odd dollars, and people have more than 3 light bulbs in their house, like commonly, right? So we have hundreds of dollars in light bulbs. Well, you can't turn the switches have to always be on. That way you control all your lights with Siri or Alexa, whatever automation thing you want to use. So she to train us, she called them training wheels. To train us not to hit the switches, we have Post-it notes over all the switches in our house. And sometimes you forget your phone, you got to go back, or she'll yell down, say, hey, can you turn the lights on up here? Does that seem better? Like, was it really that big of a problem to flip a switch? And in the middle of the night, I get up to go to the bathroom or something like that. Before, you can turn the light on in the living room so you can see, silently, right? Now I'm talking to Siri. Like, Siri, turn on the living room lights. Then Siri doesn't get it. And then so you have this 3 a.m. argument with Siri.
I feel like if you're gonna use them, you almost need to just have those Amazon Echo dots thrown throughout your house, so that no matter where you are.
Well, maybe you should mention that to my wife on Facebook. It cost me a couple $100 more.
They're like $50 a piece.
I bet you can buy them in packs too. Yeah. It's probably a discount.
Yeah. Oh yeah, on Prime Day they did some huge discount where if you bought 5, you were getting 1 free or 4 or something like that. But
why don't they do the clap thing?
Just middle of the night. Clapper. I'm surprised you remember that. And that's from like when I was a kid.
Really?
Yeah, I mean, oh, you know it's a real product, right?
Yeah.
Or what? I doubt they sell it anymore. But yeah, you could clap to make things come on and off. Like clap on, clap off, clap on, clap off. The clapper. He remembers.
I've been in a room with practical lights before. Yeah, my aunt had it.
Yeah, well, but yeah, old people.
Midday commercials are terrible.
Well, I mean, Dr. Locklear still has oil lamps like a little flint. Make sure you tell him that one. That's a good one. Okay, so let's get kicking here. So we have our for loop. Take an eye on a voyage from low to high, including high. We're going to go through should the current value of I come before the dude before him. There's no dude before him, so move forward. Should the current value of I come before the guy before him? Yes. Have I marked my pivot? I have, so we're good. Let's see. So this is going to be a 8. This is going to be, I'm sorry, a 4 and an 8, right? Did I swap my, well, I'm doing this wrong, aren't I? No, I go from low to high, pivots at 5. No, we're okay. The algorithm still works. So should I swap? Yes. For 8. Did I swap the pivot? No. Is there a guy before him? No. Because I'm now here. I've chased him, right? Remember last semester with the insertion sort, the follower? You always got it, the name of the variable is the follower, but you say it creepy like it's the follower. What does the follower do? He follows. So he goes back. So we're done swapping there. Should a 7 come before an 8? No, you know what? We're doing this wrong. I'm doing this wrong. We got our pivot at 5. I want to make sure everything before the pivot is smaller than the stuff after the pivot. We're not swapping the pivot. I'm having a brain fart here. Hold on. I mean, this will get the right answer. I just want to know if I'm doing it the right way, the consistent way. We picked our pivot. That's this guy. Well, I think we're okay. We're okay. It just felt weird what I was doing. So we'll swap the 4 and the 8. Well, we swapped the 4 and the 8 when I was here. And we'll swap the 7 and the 8. Did we just swap the pivot? We did. So we know we're done on that one. So we don't have to chase because the pivot was here. I'll go back and show you all the steps. Should this guy come before the guy before him? No. There is no guy before him. Increment I. Should this guy come before the guy before him? No. Oh, I did swap that before, didn't I? Yeah, that was just weird. Okay, should this guy come before the guy before him? No. Move on. Should this guy come before the guy before him? Yes. Swap 7 and 8. We'll probably have another variable here called the follower that knows how to follow. So this guy will follow him back. Did we just swap the pivot? We did, so we're done. That's a natural stop case for us, right? increment I, reset the pivot. Should this guy come before the guy before him? Yes, 7 and 8. Follow, did we just swap the pivot? We did not. Right? Yeah, we did not swap the pivot. We swapped the same value as the pivot, but not the pivot itself. So we're not done yet. Should this 7 come before this 7? Remember, we're doing less than or equal to. It should. The swap should happen. So we did the swap. So now I just swap the pivot. We know we're done. Increment I. Reset the follower. Should 6 come before 8? Yep. Should then we follow. Should a 6 come before a 7? Yep. Swap. Follow. Should a 6 come before a 7? Yep. Swap. Follow. But we just swapped the pivot, so we're done. Increment. Should a 9 come before an 8? Nope. So we're done. And the pivot, I think our final pivot was which one? This one? I think it was this one. It's this one. So that guy is now in his final resting place, right? Go ahead.
So when you swap those 6 and the 7 like there, since you technically swapped the pivot before that, would that not be swapped?
It should be swapped by the way we're doing it here. We swapped the pivot before that, which stopped that one, that time. So so each of these times we're incrementing I, and then we're doing some swaps. And we swap as long as we can swap or until we swap the pivot.
I was just confused because when you swapped the 6 and the 7, you're like, oh, so we just swapped the pivot, but the pivot was actually the other 7.
Well, we would have passed. We passed both of them. The 6 came across both 7s. So I think I did both of them. So yeah, I get what you're saying. Which time do we swap it? It had to be the second one, but I get your question. It's a reasonable question. I mean, technically, it's not even inaccurate because I'm showing you a hybrid quicksort. It's not even inaccurate to forget about the pivot and just bubble things up as far as they can go, because you'll still get the same result. Because that actually, what you're saying, if we made that mistake, which I'm not sure we did, would break that logic of did we just swap the pivot? Okay, so we're right here. This is our current pivot, right? That was from the previous swap. So here, that's our that's our pivot. Okay, because that guy used to be at bucket 5, and then we swapped him. All right, so that was our pivot. So now, we that's when we did the 7 and the 8 swap. So now we're here. Should a 7 come before an 8? Yes. Then we follow. Should a 7 come before a 7? Yes. So I'll just swap the 2. That way I don't have to recolor the thing. Should a 7 come before a 4? No. So we're done. Increment I. 6 come before an 8. Yep. Follow. 6 come before a 7. Yes. You're right. These were this was an issue. So by our logic up to this point, I said, did we just swap the pivot? We would stop. which is not correct. So that means that we have to remove that from the logic if we're going to do this hybrid thing, and we need to let this guy keep bubbling until he can't bubble. So we would do the swap here, 6 and 7. And then 6 should not come before the 4. So same result, but we need that did we just swap the pivot thing, which actually makes life easier, I guess, needs to get thrown out. So that's so now should 9 come before 8? No, so we're done. This was our pivot. We know that that guy is now in his final place. Do we know which of these two that guy was? I think it was. Actually, we have to reorder these anyways. So this is a 4. This is a 6. This is a 7. This is a 7. This is an 8. This is a 9 because those are changing in real memory. Then we'll mark this guy as being in his final place. Okay. Then we call Quicksort in the first half, call Quicksort in the second half. Five plus 3 is 8, divided by 2 is 4, so this is our pivot. We go from high to low. Here, let me shift this up. Oh, sorry. Should we swap there? No. So now we go here. So you see you can do a shortcut, right? You can always just add 1. You can start it to low plus 1 because you'll never actually swap before that. Also keep in mind in terms of our, and that's actually an important thing because I've been saying there's nothing here. There is stuff there. It's just stuff that shouldn't be on, we're wearing blinders here, right? Because this is bucket 3, 4, and 5. There is a bucket 2. This is bucket 2 right here. That's what's actually sitting there. So we need to be careful that we don't say, well, should this guy come before the guy before us? It never should. So it shouldn't hurt anything, but you are doing comparisons that are waste of time. So really you need to compare this. Am I at low? If I'm at low, I know a swap can't happen. So you could always just start at low plus 1 in this hybrid approach. Should a 6 come before a 4? Nope. Should a 7 come before a 6? Nope. So we can then say that our 6 is already in the correct place. That's this guy. That's this guy. Call Quicksort on the left, call Quicksort on the right. We could say the 4 is already in the right place. We could say the 7 is already in the right place because they're 1 lists, right? So we're done with this call. We'll then call Quicksort on the right half. Oop. We've got to be careful. The giant trackpad down here. Can't escape it. So pivot, high plus low divided by 2. So that's 15 divided by 2 is 7.5. Truncate, 7. So this was our pivot. We can add 1 to this. Should a 9 come before an 8? Nope. So one thing we should see here is we did a little bit more swapping than we would have done otherwise along the way with this hybrid. But we did less comparisons later on. So, you can look at a mathematical proof for this, and I think that it's one of those things where under some circumstances, the traditional way of Quicksort works. It can be faster, but I think on average, this is the better approach. And this gives you a more consistent, but keep in mind, these are simple comparisons, right? These aren't time complexity issues. So we would not do any comparisons here. So we have, here, let me color code here since we've already done these. So we would say everything's here. So we call Quicksort on the left. There's nothing on the right. That's a 1 list, so we'll say that. The 9 was already in the right place. So there's that, there's that, there's that, and there's our sorted list using Quicksort. And our calls to Quicksort just ended. Okay, let me look at something here. What have we read up to in the book? I won't give you a programming assignment so I can catch up on grading, and since we haven't written the last two of them in class yet, but I will give you a reading assignment. What have you read so far? Have you done all the searching, sorting stuff?
You've hardly done any of it.
You've done 1.3, 1.6, 1.7, but then you likely looked at Quicksort for this assignment, right? Okay. So then let's just, why don't we, since we're going to be starting list stacks and queues, why don't you go ahead and finish the sections you have not read from section 1. So the section on selection sort in Java, the section on insertion sort in Java, just so you can see the difference there. Quicksort would be a review, and then merge sort would be just to see the difference. You've seen merge sort before, but just go ahead and finish chapter 1 so we know that's done, just the exercises. And then after we write the next code, we'll start on list stacks and queues. Sound good? All right, I will see everybody on Thursday. No programming assignment, so I can catch up. So I think I'm already two assignments behind. Don't forget faculty, staff, student Bible study today. If you want free lunch, go to the cafeteria. Just write your name when you check in. You get a tray, get your lunch, blah, blah, blah. Take it down to the terrace room, and God and grub. Can't beat it.
So is Quicksort typically just used more often because? So I was just trying to figure it out. I was reading some stuff. So in merge sort, is it because we wouldn't use merge sort because merge sort can be memory inefficient because it actually requires storing sorted things in temporary arrays?
Well, Quicksort does as well.
Doesn't the partitioning kind of keep it in the same?
Well, so does merge sort.
Okay.
Yeah. Merge sort does as well. The difference, I think the answer is you're right.
Okay.
What merge sort does is during its merge step, it creates a duplicate array and then copies back.
Okay.
So it is costing more memory
Okay.
over and above.
Is that
So if
the
you
main
say
reason?
all other things are equal, yeah, and you'll see that when you read the merge sort thing.
Okay, this is all integer.